Welcome to the module 11 of the course Ultrafast Optics and Spectroscopy. In this module, we will go over ultrafast physical chemistry involved in photophysics and photochemistry. The adiabatic Born-Oppenheimer approximation, which separates electronic and nuclear motions in a molecule, is the keystone to the visualization of chemical processes. This approximation enables us to picture molecules as a set of nuclei moving over a potential energy surface created by the faster moving electrons. Despite its central role in chemical theory, breakdown of the adiabatic Born-Oppenheimer approximation is particularly common in the photochemistry and photophysics of polyatomic molecules, for which a large number of energetically close-lying electronic states and many degrees of freedom exist. Specific examples of the breakdown of Born-Oppenheimer approximation include charge transfer, electronic quenching, spin-forbidden reactions, and nature's two important basic processes, the initial radiationless energy transport step in photosynthesis and the cis-trans isomerization that initiates the process of vision. So, what does it mean by adiabatic Born-Oppenheimer approximation? We have already seen that. So, what does it mean by adiabatic Born-Oppenheimer approximation? We have, let us say, a number of electronically ground and excited states. So, this is ground state and this is electronically excited states. And if I think of how to represent the total wave function, then according to Born expansion, it is going to be nuclear wave function as well multiplied by electronic wave function, and this I going from 1 to infinity. All the possible states we have to consider. So, this is the total wave function and each I representing the electronic states. Now, if we are in the ground state, then what might happen that I have a maximum contribution coming from the ground state, and one can say that psi can be represented as this plus this plus this, which is approximately can be written as this, which means that I will be able to represent Gs multiplied by phi Gs ground state. So, one single product is perfectly fine for a situation where upper electronic states and lower electronic states are well separated. But this situation may not be valid when we extend this potential energy surface to a certain degree, and in that case we see that different electronic states, although here we have very little contribution from the upper electronic states, but in near this regime we have a almost equal contribution from different excited states. So, total wave function has to be represented then in that case like this way, and we will not be able to avoid this summation which we have seen here in the Born expansion. And the moment we do this summation, we have to write down this summation is going to be all electronic states, all electronic states. So, this only taking the product is nothing but adiabatic Born-Oppenheimer approximation. Adiabatic Born-Oppenheimer approximation assumes that most of the contribution is coming from one electronic state, other electronic states are silent, which means that I do not have much contribution from other electronic state to the total wave function. However, there are places in the potential energy landscape where different electronic states can come closer, and we can have total wave function has to be then represented by the linear combination of different electronic states which are close lying, and in that case we have to use this summation. The moment we use this summation, that breaks down Born-Oppenheimer approximation. Now, once we break down the Born-Oppenheimer approximation, what happens? We get an interesting feature in the potential energy landscape, and the feature is shown here by this conical intersection, a crossing between potential energy surfaces. Different surfaces will cross each other. So, adiabatic Born-Oppenheimer surface will never cross, but if you go beyond Born-Oppenheimer approximation, surfaces will start crossing. The breakdown of Born-Oppenheimer approximation leads to the formation of a conical intersection between electronic potential energy surfaces. A conical intersection is a point at which two adiabatic potential energy surfaces cross. While an infinite variety of intersections are possible, conical intersections can be usually distinguished from the nuclear coordinate dependence of the potential energy surfaces near the intersection. If the potential energy depends linearly on the nuclear coordinate near the intersection, the confluence is referred to as conical intersection, since the local topography near the conical intersection looks like a double cone as illustrated here. So, one can think of this is near the conical intersection is just like a double cone. And this is called photochemical funnel. Conical intersections are firmly established now to be the key features in the photophysical and photochemical processes of polyatomic molecules. They provide an efficient pathway for radiationless transition between electronic states. When a conical intersection is involved in a chemical or physical process, the nuclei move on more than one adiabatic Born-Oppenheimer potential energy surface. This process is called non-adiabatic process, and the radiationless transition between electronic states through a conical intersection is called non-adiabatic transition. The transition going through conical intersection is called non-adiabatic transition. The probability of a non-adiabatic transition is high if the nuclei encounters a conical intersection, at which point the two potential energy surfaces are energetically degenerate. So, when we think about the photoexcitation process here as shown here, A is excited to a star, electronically excited states, and then it will evolve on the potential energy surface. But there is a chance or probability having this transition at this point of nuclear coordinate. This nuclear coordinate corresponds to this point at this point, but the probability is very low as compared to the probability here, because they are degenerate at that point, and I'll let you know why it should be, the probability would be high at this point of regime. In general, a number of intrinsic issues are associated with non-adiabatic chemistry and physics through conical intersections. All these issues can have significant influence on understanding molecular photophysics and photochemistry on ultrafast time scale. Our early thinking about non-adiabatic transitions between different electronic states was dominated by the application of Fermis golden rule in the context of energy level diagrams as illustrated here. This kind of diagrams we have seen in our textbook before, and this kind of diagram was used to explain different processes following photoexcitation. So, this vertical line represents the photoexcitation. That photoexcitation can lead to first IVR, to the coming back to the lowest ground state of the S1 excited state, and then I can have internal conversion, which is represented by IC, from S1 to S0. And that internal conversion is nothing but a non-adiabatic transition, and previously this kind of non-adiabatic transition has been discussed in the picture of Jablonski diagram. And finally, the non-adiabatic transition rate, which is derived from Fermi's golden rule, is given by this equation, where I and F refer to the initial and final vibrational eigenstates on the S1 and S0 adiabatic Born-Oppenheimer electronic potential energy surfaces respectively. The matrix element VIF, this matrix element VIF represents the electronic coupling between these adiabatic Born-Oppenheimer states. Finally, the density of states of S naught at the given energy E is denoted as rho E. Fermi's golden rule is derived from perturbation theory and is valid as long as the coupling between electronic states are weak. Only detailed knowledge of the final vibrational eigenstates would allow one to extract any information about product branching ratios in the process following photoexcitation. This requires complete solution of the vibrational Schrödinger equation, which is impractical for most polyatomic molecules. Therefore, direct quantitative use of Fermi's golden rule to describe non-adiabatic processes of polyatomic molecules is practically impossible. So, what is more realistic picture which came up after Fermi's golden rule based Jablonski diagram? The more realistic picture which is describing the non-adiabatic process is to include non-adiabatic coupling term, which is discussed here. In order to describe the processes following photoexcitation, a more convenient theoretical framework should definitely go beyond the Born-Oppenheimer approximation. This allows non-adiabatic transitions between different electronic states by introducing the terms neglected in adiabatic Born-Oppenheimer approximation. They are called, so the moment we have taken that, we have neglected that summation, we have neglected many other terms which are not shown here through derivation, but many terms which are neglected. And we have to now rethink of those neglected terms. They are mostly called non-adiabatic coupling term, which is given by this. What does it suggest? It suggests that this psi f and psi I are the electronic states of final and initial states. So, there are two states which are coupled with each other. This is your final state, this is your initial state. These are electronic states. Electronic states are getting coupled by nuclear coordinate or nuclear motion, that is capital R representing the nuclear motion. And this is the essence of non-adiabatic coupling. Two electronic states are getting coupled due to nuclear motion capital R. This equation highlights that non-adiabatic coupling term becomes infinite near a conical intersection, which is a singular behavior, because near conical intersection EI is going to be EF. So, coupling would be infinite. Thus, when a conical intersection is present, integrals over the nuclear coordinates involving non-adiabatic coupling terms will be dominated by the geometry near the conical intersection, not by geometry near the FC point. So, FC point is the point where the initial photoexcitation occurs, which is the vertical excited state point, and conical intersection point is here. So, what is the idea here is that because the energy difference near the FC point would be very high, that is why non-adiabatic coupling term would be very low, and in that case one can neglect non-adiabatic coupling term in this regime, in the FC regime. But the moment it is the system is evolving to the conical intersection point where I can have a maximum the contribution coming from the non-adiabatic coupling term, we have to consider this non-adiabatic coupling term. We cannot neglect it, and we cannot assume what would be the non-adiabatic coupling at the conical intersection following an FC point geometry. We have to get the right geometry near the conical intersection and then predict what would be the non-adiabatic coupling. If the geometry corresponding to the conical intersection is quite different from that at the FC point, the form of the nuclear wave function and electronic coupling in the CI regime will be poorly approximated by low order approximations around the FC point. This low order expansion of a potential energy surface around its FC point is often used to evaluate VIF in Fermi's golden rule. Thus, even if the Fermi's golden rule is strictly valid, the subsequent approximation used to evaluate VIF becomes questionable, and quantitative application of the FGR approach to the unimolecular photochemistry and photophysics is difficult. In many polyatomic molecules of photochemical interest, the relevant conical intersections are in need far away from the FC point, and the Fermi's golden rule approach with the usual approximation is not appropriate. Detailed non-adiabatic theory is more appropriate to describe non-adiabatic processes. In general, these electronic non-adiabatic processes are mediated by conical intersection. So we'll take a look at it in details, but through the simple math. If we have, let's say, two states, one is phi 1, another one is phi 2. There are two states we have, and we'll consider that our wave function has to be written. So if we had two states under Born-Oppenheimer approximation, we would have written psi equals phi 1 and chi 1. That is the nuclear wave function, electronic wave function. The product of nuclear wave function and electronic wave function would represent the total wave function. This is the Born-Oppenheimer approximation. But we don't want to use Born-Oppenheimer approximation. We want to use Born expansion, which will be including the full non-adiabatic theory. In that case, psi has to be, total wave function has to be represented as C1 phi 1 expansion coefficient plus C2 phi 2. Both states we have to include together. In thermal reactions, in general, molecular structure associated with the transition state. So we think about a transition state and we say this is energy versus reaction coordinate. And they are going through the transition state. This is reactant, this is product. When they are transforming from reactants to product, they go through this transition state, and generally thermal reactions are predicted with the help of the transition state. Similarly, in photochemical reaction, geometry associated with a conical intersection is often found to be related to the expected photoproduct. So that's why if we want to find out, okay, what is the outcome of the photo excitation, then we have to think about the conical intersection, and and through this conical intersection only we will be able to predict what would be the photoproduct in a photo excitation process. For diatomic molecule where only 1 degrees of freedom I have, that is the bond distance, electronic states with the same symmetry do not cross, yielding a non-crossing rule. So what is the origin of this non-crossing rule? We'll go over it right now. To understand the non-crossing rule, we'll consider a diatomic molecule with two electronic potential energy curves. Mathematically, two electronic states are represented by phi 1 and phi 2. And we have to, as I mentioned, this is the Born expansion we have to take. So the total wave function has to be represented by this way. So we can insert this in the time independent Schrodinger equation, H psi equals E psi, and we'll be able to rearrange this equation a little bit, and we get this expression. Now what we have done, we have used orthonormalization condition to reduce this equation. This is often we use. I'll remind one more time. In our previous modules, we have used this kind of condition to reduce quantum mechanical equation. So let's say I have phi 1 plus phi 2, this kind of wave function. If I have this kind of wave function, then I can multiply with phi 1 first, phi 1 star, and if I multiply, then what I get is phi 1 plus phi 1 phi 2, and this we know it is going to be 1, and this we know this is going to be 0. So this is the way we can reduce this equation. So, in many occasions in quantum mechanics, we use this orthonormalization condition to reduce the equation further. So, here we are doing the same thing. We are multiplying in this step we are multiplying with phi 1 star, and the next step we are multiplying by phi 2 star. And if we reduce that further, we get this expression, and it's easy to follow. And then after this expression, what we are going to write is that will decompose this total Hamiltonian into its kinetic component and electronic component. We are separating it. The moment we do that, then what we get is that this integral becomes 0, and this integral gives me E1 electronic energy. This integral becomes 0, it's because I have, let's say, phi 1 square d dr. If I have this, then I'll write 2 phi 1 d dr phi 1, and what I have is this phi 1 square is always going to be 1. So, phi 1 square, if it is normalized, then it's going to be always 1. That's why the first derivative with respect to r is always going to be 0. So, finally, this expression is nothing but 0, and Tn is nothing but d dr. Is related to the derivative with respect to r. In fact, this is the second derivative. So, it is the second derivative, but if we consider the first derivative is already 0, the second derivative is going to be 0 as well. So, these terms will be always 0. Similarly, here this term will also be 0. This term will also be 0, because here I have orthonormalization 0, but this term may not be 0. So, finally, we reduce all these equations to these two equations, these two linear equations, which can be solved. We can get a non-trivial solution for the secular equations. We have the secular determinant to be 0. And if secular determinant is 0, then I have the final expression for E plus minus 1. There are two values of E we get. If we have expressed the total wave function as summation of C1 phi 1 plus C2 phi 2. This means that due to coupling of phi 1 and phi 2 electronic states via nuclear motion, that is non-adiabatic coupling, we get the energies of two states as E plus. So, one state is going to be E plus and another state is going to be E minus. In absence of non-adiabatic coupling, that is, if I make this to be 0, then what I get? I get always E plus and E minus is going to be always E1 electronic energy and E2 electronic energy. Always we are getting adiabatic states. But what we are interested in, knowing a point on the potential energy landscape where I have E plus equals E minus. And in order to satisfy this condition, I have to have two conditions satisfying simultaneously. What are the conditions? The first condition is going to be E1 electronic minus E2 electronic divided by 2 square is 0, and then T12N is 0. Both we have to satisfy simultaneously. Now, for diatomic molecule in which one nuclear coordinate we have, only variation we can change the potential energy surface we can change the potential energy with the help of only one variable. What is that variable? Internuclear distance. So, for diatomic molecule with one internuclear distance, fulfilling both conditions is extremely unlikely. This occurs if the two adiabatic electronic states have the same symmetry. If I have the same symmetry, then Tn is symmetric always. So, in order to vanish the integral phi 1 Tn phi 2, if phi 1 and phi 2 have to be antisymmetric. So, for diatomic molecule, this condition can be fulfilled if phi 1 and phi 2 are antisymmetric. Otherwise, they will not fulfill. So what happens if for diatomic molecule only two potential energy surfaces may approach each other and then they may not cross. This is called avoided crossing. And this occurs when phi 1 and phi 2 symmetries are the same. But if their symmetries are not same, then they can cross each other. And if they are crossing each other, then this crossing point is called conical intersection. For polyatomic molecules, we have many degrees of freedom, bond angle, bond length, many things. And that's why, because of the many degrees of freedom, we can very easily get this degeneracy, because these two conditions can be fulfilled very easily. Near degeneracy, the topography of the surfaces features a double cone meeting at the point of degeneracy. Adiabatic energies varies linearly with coordinate near the conical intersection. The space which uplifts the degeneracy is called branching space or GH plane. Orthogonal to the branching plane is the intersection space in which the degeneracy is not lifted, constructing conical intersection seam. At each point of the seam, there is a conical intersection. Thus, at a conical intersection, one can distinguish two directions, G and H, such that if one were to plot the energy in the subspace of these two geometric variables, the potential energy would have the form of a double cone in the region of the degeneracy, shown here. Thus, the GH internal coordinates lifts the degeneracy linearly near the conical intersection, which is shown here. These two double cone present, and this if we plot near the conical intersection, if we plot the GH plane, or if we plot the GH coordinate as a the energy as a function of GH coordinate, then we get this double cone feature. Conical intersections are also called photochemical funnels, provide pathways for ultrafast internal conversion or intersystem crossing. Here, a number of general phenomena of ultrafast non-adiabatic dynamics through the conical intersections are discussed. Electronic excitation promotes a molecule from its ground to an electronically excited state. Here, the nuclei in the electronic ground state are assumed to have their positions characterized by point P dash in the reaction coordinates. So, this is my ground state P dash. Electronic excitation takes place so fast that nuclei do not have enough time to move, and that's why it is called vertical transition, vertical excitation occurs. The quantum mechanical analog of the classical Frank-Condon rule is that the probability of nuclei making a transition from one potential energy surface to another is greatest for these places. So, when I have a vertical transition, we have to think about, either we classically can think of that nuclei doesn't move, so I have this preserve this coordinate r. And quantum mechanical version of this same idea is that I have the maximum overlap between the vibrational states which are undergoing the transition. The nuclear configuration at the Fc point of the upper excited state may differ quite significantly from the nearest potential energy minimum, which is m star given here in the excited state potential energy surface. In a few tens femtoseconds, the system slides down from Fc to the neighborhood of the m star, transforming its potential energy into kinetic energy. This occurs because of the force dVdr on the nuclei due to the change in electronic configuration from S0 to S1. If M star is separated from conical intersection by a barrier, as soon as the molecule during vibration overcomes the barrier at the transition state by going over it or by tunneling through it, it will be driven by the new force to the conical intersection attractor, and often it is going to be 100% probability of transition near the conical intersection. At the conical intersection, the molecule undergoes a non-adiabatic or non-radiative transition to the ground state of the intersection of the potential surface. If the relative momentum of the nuclei is large enough, the system slides down along pathway towards P, the nearest minimum of the product. If the momentum is small, the system may go back to the P dash, returning to the original molecule. So at this point, I can have two possibilities: going back to the reactant side, going to the product side. The total energy, of course, has to be conserved. In a condensed phase environment, the system finds a way to dissipate its energy, transfer an excess of electronic energy into its own molecular vibration, rotational and translational degrees of freedom, or to those of the neighboring solvent molecules. Under gas phase isolated conditions, however, the excess electronic energy following a non-adiabatic transition through a conical intersection is stored in the vibrational degrees of freedom on the ground electronic surface, which can often cause molecular fragmentation or rearrangement. Topographical structure of potential energy surfaces near a conical intersection may mediate either a non-adiabatic photophysical process, which is purely internal conversion, or non-adiabatic photochemical process. Three basic types of photochemical reactions pathways are often found for organic chromophores. They are shown here. Path A, here by this path we are showing that photoexcitation can lead to successful photochemistry because of the feature of the conical intersection we have here, for which a finite percentage of absorbed photon energy is used to produce a different chemical species. In path B, if I have a feature like this, then what might happen, because of this photoproduct may come back to the reactant side, and that can introduce internal conversion only. And path C, what we see here, it can abort photochemical reaction near the conical intersection because it is directly coming back to the reactant side. So what is the topographical feature of conical intersection and overall excited state pathways that controls the photoproduct or the internal conversion? The development of femtosecond pulse laser has made it possible to make observations on transient species which have very short lifetime. With respect to the lifetime, the transient species formed near an avoided crossing or conical intersection in photoinduced processes may quite resemble an activated complex or transition state which we used in thermally activated processes. We shall go over now the ultrafast relaxation dynamics through an avoided crossing for a well-known example, isolated gas phase sodium iodide system, which exhibits covalent to ionic avoided crossing. Here we have shown NaI, sodium iodide potential energy surfaces. Electronically ground and first excited state of NaI molecule is described with two potential energy curves. One is ionic, the first ground state is ionic, and excited electronic state is actually covalent in nature. When I say ionic, NaI, Ionic means most of the electron cloud is shared by iodine, and covalent is attracted to. So for when I say ionic, most of the electron density is attracted towards I. That's why it gets I minus and sodium plus. And here covalent means it's equally shared. The electron density is equally shared. So these are the two different kind of bonding, nature of bonding, and both nature, extent of ionic contribution and extent of covalent contributions, they all contribute to the overall bonding of any molecule. NaI particularly is an example where ground state showing ionic potential and another excited state is showing covalent potential. Both curves create an avoided crossing at an internuclear separation of approximately 7 angstrom. In the ground state, the NaI molecule exhibits ionic electronic character, and the same molecule features covalent electronic character in the first electronically excited state. However, because of difference in ionization potential of Na and Na plus and electron affinity of I and I minus, dissociation limit for Na plus and I minus is greater than that of Na plus I. So this dissociation limit is higher than this dissociation limit. NaI is a heteronuclear diatomic molecule which does not possess a center of symmetry. Hence, symmetry argument does not help two electronic potential energy curves to cross, rendering avoided crossing. Because of this avoided crossing at internuclear distance approximately 7 angstrom, electron harpooning occurs when the molecule is bound on the upper electronic state. This suggests that electron is transferred from one atom to another during vibration on the upper excited curve as the electronic character changes from covalent to ionic in the bound upper curve. However, if there is a non-adiabatic transition from upper state to the lower state through the avoided crossing region, which ultimately results in dissociation, molecules does not need to. However, if there is a non-adiabatic transition from upper state to the lower state through the avoided crossing, then molecule does not need to change the electronic character. It is always covalent. So basically the covalent curve after crossing looks like this, and ionic curve after crossing looks like this. In the femtosecond pump probe spectroscopy, the pump pulse at lambda 1, which is center wavelength, excites the molecule from ionic ground state to the covalent excited state. And because we are using a broadband source, which is a femtosecond pulse, we are exciting simultaneously many vibrational states in the upper excited state, and which is creating the wave packet. We have shown previously what is the origin of the wave packet. Consequently, electronically excited complex exists as a superposition of many vibrational states, which renders a localized vibrational wave packet. There are two limiting possibilities now following electronic excitation. The vibrational wave packet of the electronically excited NaI may get trapped on the adiabatic potential energy curve. So I have the adiabatic potential energy curve, and I can have this wave packet which I have created. It can be trapped, and if it is trapped, it is then going to oscillate within this adiabatic curve. Or there is another possibility: the vibrational wave packet may dissociate, shown as the movement of the wave packet towards the very long and internuclear distance. So in that case, wave packet may actually dissociate, and it can actually propagate along this way through this non-adiabatic transition only, and I can have a dissociation. These two possibilities should exhibit entirely different temporal behavior, and if there is a trapping, the details of the nature of the curves and the strength of non-adiabatic coupling near the avoided crossing can be deciphered from femtosecond pump probe spectroscopy. In the femtosecond pump probe spectroscopy, the dynamics of the vibrational wave packet is probed by a second probe pulse Probe excitation essentially creates molecular ions with frequency that corresponds to absorption frequency of perturbed Na. So I have now used pump probe. We have here pump probe spectroscopy. The pump is exciting the molecule to the excited state. This experiment was performed by Amazuel group, and femtosecond pump pulse was selected at 310 nanometer, and the probe pulse was selected from the wavelength range of 560 to 630 nanometer. And here 310 nanometer is enough to excite NAI system to the electronically excited state, and we have to remember that 589 nanometer is only on resonance with free Na D line, sodium D line. But other probes, like other than 589 nanometer, all other wavelengths are off resonance with free sodium atom, but they are on resonance with perturbed sodium. So weakly bound sodium species with iodine, they are on resonance, and that's why we can actually look at the molecular ion or the fragment. The observed parent ion intensity, this is the parent ion intensity, this is parent ion intensity as a function of pump probe delay time is plotted here, which shows oscillatory behavior that reoccurs in about 1.25 picosecond, featuring the wave packet oscillation with about that period. This period corresponds to a frequency of 27 wave number. The decline of intensity, slow decline of intensity, shows that the rate at which excited state species dissociates via non-adiabatic jump from upper curve to the lower curve through the avoided crossing. Furthermore, the complex survives for about 10 oscillations, and the oscillations are damped in 10 picosecond. Therefore, the average probability of non-adiabatic transition through the avoided crossing is estimated to be 0.1. Similar probability of non-adiabatic transition for NAI was also predicted by Landau-Zener curve crossing calculations. For NABR, another system, when we consider NABR, we see that the frequency of oscillation is found to be similar in magnitude. However, severe damping is observed. It barely survives one oscillation. Therefore, the result evidences that the probability of non-adiabatic transition through the avoided crossing for NABR is more than that for NAI. This is consistent with the mass dependence of non-adiabatic coupling term. Large mass exhibits small non-adiabatic coupling term, resulting in slow non-adiabatic transition through the crossing. With this, we have come to the end of this module. In this module, we have discussed the origin of conical intersection, consequences of conical intersection, how to represent conical intersection, how to think about or how to predict photochemical behavior of a molecule through conical intersection. And then we have given an example of ultrafast spectroscopy, which has probed the dynamics of NAI system evolving through an avoided crossing. We'll meet again for the next module.